What's up, guys? Welcome back to the 12 ISLs of Christmas. Today we're going to be looking at our sixth problem, 2023 ISL A2. The problem states that if R is a set of real numbers, and we let f from R to R be a function such that f of x plus y times f of x minus y is greater than or equal to f of x squared minus f of y squared, and that the inequality is strict for some x0 and y0, we want to prove that f is always non-negative or always non-positive. So the one thing that stands out the most is this condition here. So why is this special? Well, if the problem condition did not hold true, that means that the inequality was never strict. Then we have f of x plus y, f of x minus y is equal to f of x squared minus f of y squared. And then we can just note that f of x equals x satisfies this. But then f of x is greater than 0 for x is greater than 0, but less than 0 for x is less than 0. So that breaks the problem statement. So this condition that's given in the problem is definitely necessary. So let's see how to use it. But first we need to figure out some basic stuff regarding the problem. Well, if we plug in x equals y, because then that will eliminate this side here, we end up getting f of 2x f of 0 is greater than or equal to 0. Well, are we just done? Because we can just divide by f of 0 and we're done. Well, not quite. We can only do that if f of 0 is not equal to 0. But in the case where it's equal to 0, then we cannot divide by 0. So in the case when f of 0 is not equal to 0, then we just divide both sides by f of 0, and we get that f of 2x is greater than equal to or less than or equal to 0, depending on the sign of f of 0, and we'd be done. But if f of 0 equals 0, then that means that we divide by 0, which is not allowed. So we just need to solve the problem for this case. So now that we know that f of 0 equals 0, we want to somehow use this and make one of these sides equal to 0. Well, let's consider the left-hand side. Because if one of these terms is equal to 0, then this entire left-hand side is 0. Let's try setting f of x minus y equals 0. Then we want x minus y equals 0, but we've already done that to get that f of 0 equals 0. So let's try the other case, where x plus y equals 0, so that y equals negative x. So when we plug this in, we get that f of 0 times f of 2x, which just becomes 0, is greater than or equal to f of x squared minus f of negative x squared. Well, this should come across as striking, because why can't we just plug in negative x now? Because then we get 0 is greater than or equal to f of x squared, or negative x squared, minus f of x squared. And that means that f of x squared is less than or equal to f of negative x squared, but also f of x is greater than or equal to f of negative x squared. So that means that the two must be equal. In other words, f of x squared is equal to f of negative x squared. Notice how we use the idea of swapping x and negative x to show that this was true here. So let's see what this approach does in general. So we get the inequalities f of x plus y, f of x minus y is greater than or equal to f of x squared minus f of y squared, but also f of y plus x, f of y minus x is greater than or equal to f of y squared minus f of x squared. So if we add the two together, we end up getting f of x plus y, because that's a common factor, and f of x minus y plus f of y minus x is greater than or equal to 0. Now, we know that these two are either equal to each other or they are additive inverses of each other. since we know that f of x minus y squared equals f of y minus x squared by the claim. So what can we do now? Well, we can just take cases on what happens here. Because if f of x minus y equals negative f of y minus x, then this just becomes 0, and this is obviously true. So we need somehow for this to not be 0, because if this were true here, then we would have that one f was either positive and one was negative, or we would have that this would always have to be 0. So we want the case where this happens to be impossible, meaning that we need to somehow have that this is strictly greater than 0. So we need a strictly greater than sign in one of these inequalities. But then this is where the problem statement comes in. Assume that the inequality is strict for some x0, y0, and r. So we can just get rid of all of this and rewrite the inequalities in terms of r, x0 and y0. We get f of x0 plus y0, f of x0 minus y0 is greater than f of x0 squared minus f of y0 squared. And similarly, f of y0 plus x0, f of y0 minus x0 is greater than or equal to f of y0 squared minus f of x0 squared. And then adding the two gives f of x0 plus y0 squared times f of x0 plus f of x0 minus y0 plus f of y0 minus x0 is greater than 0. And this should not be squared. So now what can we do? Well, if f of x0 minus y0 was negative of this, then this would evaluate to 0, which is bad. So that means that f of x0 minus y0 is equal to f of y0 minus x0. And that's pretty good. And furthermore, we know that it's not equal to 0, because if it were equal to 0, then this just collapses. So this is not equal to 0. And this seems pretty useful to us. So let's go ahead and write it as follows. We can write this as b, so that f of b equals f of negative b is not equal to 0. And this goes inside the list of information we have in the top left corner. And this, we want to somehow use this because this is otherwise not very true when we have f of x equals x and inequality is not strict anywhere. Because if f of x equals x, then the only way that f of b equals f of negative b is if b equals 0, but then that breaks. All right, so let's see how we can use this. Well, for starters, we want to let f of one of these guys equals b so that we can better understand what's going on. So if we let x plus y equals a and x minus y equals b, then we get f of a times f of b is greater than or equal to, if we solve for x and y, we get x equals a plus b over 2 and y equals a minus b over 2. But those don't matter for us, because then we end up getting f of x squared minus f of y squared. And similarly, f of negative b, by swapping the variables, is greater than or equal to f of y squared minus f of x squared. So we add the two and get f of a times f of b plus f of negative b is greater than or equal to 0. But then recall that this is not equal to 0, and f of negative b equals 2 f of b. So that means that f of a, f of b is greater than or equal to 0 for all a in the real numbers. At this point, we are done, because if f of b is less than 0, then that means that f of a must also be less than or equal to 0, because otherwise positive times negative is negative. So that means that f of a is less than or equal to 0 for all a. And similarly, if f of b is greater than 0, then f of a is greater than 0 for all a. And this solves the problem. So what's the main takeaway from this problem? Well, our main motivation came from trying to use this rather strange problem condition, that the inequality is strict for some x0 and y0. And from there, we try to see what happened when we swapped variables, because that gave one of the earlier claims of the problem, namely this. And by swapping the variables, we could see how to use this strict inequality to get this pretty interesting claim that would otherwise not be true for a function f that such that the inequality is not strict and equality holds everywhere. And by using this, we were able to do some more variable swapping and get this really neat inequality. And from there, we're done. So the moral of the story is to always be on the lookout for your given information and try using that to your advantage. Whenever you're whenever you're in the middle of an Olympiad problem and you're stuck, it's a good idea to think, what piece of information have I not used here? At this point, we got stuck here and we asked, what piece of information did we not use? And we didn't use this here. And when we use that piece of information, we got this, which was enough to finish the problem. So thank you so much for watching this video, and I'll see you guys tomorrow for the next one.